We're on the hydrolysis assignment, and we've got a problem here that it's kind of annoying, actually. It's the one that's got this image of the textbook, all right? And the reason this problem is annoying is because the answer choices choose several of these different salts that could each be the answer. So depending on the order that you check each of the salts in is going to determine how long this problem takes. Now, a couple things that I see it gives me, though. It says that the salt is unknown. That's what it wants me to find. But it says that there is 0.1 moles of it. All right, and that 0.1 mole of it is existing in 1 liter. So this was almost annoying because it didn't give me molarity, but since the liters is 1 and molarity is moles over liters, it's this divided by 1, which will give me 1. So this information isn't even needed because this right here will be a concentration. So that's good news. But the only difference between all the answer choices is going to be the given KAs. So let's just set up the part of the rice table that we know will absolutely be true. All right, so we know that something, I'm going to leave the very first part blank, but we know that some weak ion is going to be reacting with water because that's what happens in hydrolysis. All right, and whatever that item is going to be a proton acceptor for sure, because we know that it is a hydroxide containing solution. I know it's hydroxide because another part of the given information is that the pH equals 8.08. This is a basic pH, which means it must be a basic solution. So I know for sure that that's going to be my that the hydroxide will flourish. So as I look over the answer choices and I compare to that book page, I can see that there's basically a bunch of different Ka values that are given. So I could go one by one and put the weak ion there with what would form over here. All of them, though, are going to have an initial concentration of 0.1, all right, with nothing here and nothing here. All right, and when I say here, remember, there is another item that's going to form here. But I mean, it'll be a Bronsted-Lowry association based on whichever of the answer choices we're picking. So again, I'm just trying to fill in everything that's going to remain constant, no matter which answer choice I'm checking. So we know we're going to shift towards those two zeros, and I plus C equals E. And for this video, I considered, okay, well, let's just try a wrong one and show them what a wrong one looks like. But all of the steps are repetitive. So I'm just going to identify the correct answer and then show you how the work matches up. And if you were to do the exact same work on any of the wrong answers, it wouldn't equal that pH of 8.08 that you need it to. So it turns out of all of the options, the correct answer is sodium fluoride. All right. So this is the guy that I'm just going to check off the bat. But why is it sodium fluoride? Well, if I take a look at the book page, the only of the ions or only of the acids there that uses the F minus, all right, because that F minus right there is weak. All right, in this compound, it would be the parents would be sodium hydroxide and hydrofluoric acid. All right, if I were identifying parents, this is strong and this is weak. So while doing my analysis, it would be the weak ion that gets added to the rice table, right? And that's how you'd have to think through all of the choices. But it turns out that the given Ka of the HF from that printed book page is 7.2 E negative 4. And I'm reading that, I mean, that's another given number. All right. Now, I'm going to work through the work and show you how my pH of 8.08 happens here. But realize, like in all hydrolysis problems, there's a mismatch because OH is what's flourishing, but Ka is what I'm given. So I'm going to fix that by saying Kw of 1 E negative 14 divided by Ka of 7.2 E negative 4, 1 E negative 14, yeah, right about 7.2 E negative 4. All right, and it looks like that gives me 1.4 E negative 11 as a Kb. And of course, Kb is what I'm going to put into my equation here. So if I'm going to go in, remember it's going to be products over reactants. Oh, I'm sorry, I didn't fill my friend in up here. Of course, this H moved over here, so this is HF. Not that that affects too much because we're focused on the hydroxide values here. But it's going to be products over reactants. So I'll go 1.4 E negative 11 equals my products, or these two X's, over my reactant, which is 0.1 minus X. I'm going to simplify this, and I'm going to get X squared equals, this will distribute, which is going to come out to 1.4 E negative 12 on the first distribution, minus 1.4 E negative 11X on the second distribution. I'm going to turn this into a 0 equals for my solver. So it's going to be 0 equals, I'll keep the X squared positive and swap the signs of everything else while I make it quadratic. So this is going to be 1.4. I'm going to do the X expression first. E negative 11X minus 1.4 E negative 12. All right, so let's enter that into the solver, math. Solver, 0 equals X squared plus 1.4 E negative 11X minus 1.4 E negative 12. Put in my guess there and solve. And it looks like, remember we have an absolute value, it looks like it's going to be 1.2. Now look, not only is it an absolute value, look, my scientific expression is hidden over here because it is 1.2 with sig figs, but it's 1.2 E negative 6. See it hiding over there? So be careful. So X is 1.2 E negative 6 molar. And X, of course, is the hydroxide concentration. All right? But I'm trying to line up with this pH because if this is the right salt, which it is because I'm cheating, but if it's the right salt, when I'm done doing this, it's going to equal my pOH of 8.08. So I don't want an OH concentration. I want a pOH. Again, I can use KW. That's not KW. Which is 1 E negative 14 divided by the OH of 1.2 E negative 6 is going to give me an H plus concentration. All right, so the video paused because hang on, y'all. I'll probably have to continue this in a second video because life is cool.